When we were graphing and plotting out our term values for our sequences, specifically for arithmetic sequences, there was a note that was mentioned that it looks very similar to linear equations. So we're going to explore that relationship and see if we can truly use our linear equation expression of y equals mx plus b to define sequences. Would that be a valid way to quickly write a sequence expression? Well, in the first one, we have a sequence of 5 numbers. It starts at 6, goes to 14, 22, 30, and 38. And so the first thing that we need to do is say, is this an arithmetic sequence? Yes, it is, because as we notice that every time we jump, our jumps are adding 8 each time. So our typical formula that we have says that to find any number of this sequence, any term value, I can take the first term, which is 6, and I can go a certain number of jumps, one less than my terms, by however much I'm jumping. So in this case, we have a sub n equals 6 plus 8n minus 8, and I have my value is equal to 8n minus 2. So for any term, we've also looked at how that can also be reflected as f of x would equal 8x minus 2. So to find the y value, or to find the value at that location, we would do 8 times whatever location we're at minus 2. So let's look at the second one. We've got 9, 23, 37, 51, and 65. Each time we are jumping by 14. So again, we're going to use our generic sequence equation and say that for any value that I'm plugging in, it's where I start. In this case, it's 9 plus 1 less of what where I'm going for my jumps, and I've got 14. So in this case, I've got a sub n equals 9 plus 14n minus 14. So a sub n is going to equal 14n minus 5. And those are our generic equations for these sequences. So if we were to graph the points here, this is term 1, term 2, term 3, term 4, and term 5. We have 1, 2, 3, 4, 5. At 1, we would be, let's say 6. That would be 12, 18. Let's see where we're at. Then at 2, we would be at 14. At 3, we would be at 23. And we would see that indeed we do make a line as we graph these points. The important point to look at is that our change, the change along our x, so the change along our x is always going to be 1. Because we're going from 1 to 2 to 3 to 4 to 5. We're never skipping a turn. So our change in x here between points is always going to be the value 1. And if we look at slope, we know that slope is the change in y over the change in x. So we're going to have some change in y value over our change in x, which we know is currently 1 and will always be 1. And our 1 doesn't ever really have to be written. So our slope is simply going to be defined as our change in y value. And if we look back up, our change in y value is the amount that we are jumping by if we had graphed it. So could this just be plugged in as slope to an equation? Let's look at it. So if we have the same exact points, and we were to go back, because we know that for our slope-intercept form, we have our slope, which is our change in y value over our change in y over change in x. And our b value is our y-intercept. Well, what is y-intercept? Y-intercept answers the question when x equals 0. Well, currently we are always starting at x equal to 1. We're always starting with the a sub 1 value. So how would I find my a sub 0 value? which would be when x equals 0. To find our a sub 0 value, we know that this is a sequence, so we know there's consistency with our jump. So if I move up by 8, if I find the number before, I'm going down by 8. So 6 minus 8 gives me -2. If I were to plug in these values, I know my change in x is always 1, so it can simply go away. My change in y is 8, so I'd have y equals 8x. What is my y-intercept? What is the value when my x location is 0? My value is -2 in that case. So we have come up with any y value, which could be written as a sub n. Any term value is 8 times that term, because this is really f of x, minus 2. And let's see if we have consistency. 8n minus 2. 8n minus 2. We got the same answer, so it seems to be true. Let's look at this last one. When we did this bottom one, we said that we were jumping by 14. We used our sequence equation, and we came up with the formula saying that a sub n is 14n minus 5. So let's address that as a linear equation as well. So we know that 9 is our a sub 1. This is our location when x equals 1. We are going to be at 9 here. So if this line is consistent because my change in y is always going to be 14, my change in x is always going to be 1, so that means my slope is 14 over 1. But I need a y-intercept to be able to fill in my b. So if at 1, it's at 9, where is it located if it's at 0? So we have to go backwards and find that a sub 0 term location. Well, if I added 14 to get to 9, then I have to subtract 14 to go back. So I've got -5. If I were to write this in my linear equation, I would now say f of x is equal to my slope, which I know is change of 14 over change of 1, plus my y-intercept, which is -5. So I could rewrite that to find any term along this. I have 14 times that term location minus 5, 14n minus 5, 14n minus 5. So we are able to see that by using our sequence equation and to find our generic, it is the same as backing up, finding our y-intercept, our x equals 0, a sub 0 location, that term time plus your slope gets to be plugged in with your slope times each term value that you get. So that's our proof that our sequence equations, the expressions to find any term, are identical to the slope of the line through all of the points.